So this is lecture 3 on differential forms. There are two main things I need to explain here in order to really make sense of what a differential form is. The one is the wedge product, the other is the so-called exterior differential. So we already saw the first part of the exterior derivative last time when we talked about how to take a function and take its differential. At each point P, that gives us a dual vector, and then if you assign a dual vector at each point, that gives us what you might expect would be called a dual vector field or a covector field, but in fact we call that a differential one form, or sometimes just simply a one form. Now, I say a differential one form to emphasize we're building it with differentials. You could think about just taking an abstract vector space and taking wedge products of those vectors. Those would give you other objects. But our focus here is really on the exterior calculus, as it's called. And so that means we want to talk about differentials of functions, and so building things with dx's, dy's, dz's in 3 dimensions. So before we can do that, we need to understand what is a wedge product. Well, a wedge product it's a very specific kind of product that you can build over a vector space, all right? It has 3 main characteristics. The first, and perhaps most important, is that it's associative. The wedge product is an associative product. We build it in this way. Alpha, wedge, beta, wedge, gamma. Makes sense. I could put the parentheses on the last 2 or in the first 2. Anyway, we get the same result. The next thing is it's anti-commutative on differentials. So, or in more general, you could say on a basis, all right? This axiomatic system is nicely presented in, I think it's Curtis's Abstract Linear Algebra, if you want to read from a more algebraic perspective. Not too sophisticated, but just right anyway. So it's anti-commutative on differentials. In other words, when you commute the order of the wedge product, we switch the order of dxi and dxj, you get a minus. And then 3, it's distributive. So alpha wedge beta plus gamma is alpha wedge beta plus alpha wedge gamma. If there was a constant, if there's a constant somewhere, like say here, I could pull it out like that. It's also that. So in other words, the wedge product behaves like usual, like a multiplication, all right, with one little exception, the minus when you swap the differentials. I say like usual, that's not entirely honest, of course, because the cross product is a usual thing we think about, right? But the cross product is not associative. This right here looks like the cross product, right? But this actually is not true for a cross product. If you have a textbook which writes cross products of 3 things without parentheses, you should really wonder if they know what they're doing. I do. I have some such books. Anyway, that said, once you have the anti-commutativity for the differentials, you can easily extend it to arbitrary one forms. An arbitrary one form is built with coefficients, which are functions, alpha I and beta j for alpha 1, all the way to n, beta 1, beta n. These are functions, okay? And if I look at alpha wedge beta, I'm going to be able to show that that's equal to minus beta wedge alpha. Let's see how. So alpha wedge beta, I have alpha wedge beta, like so. And then that I can use distributivity to pull the coefficients out front, right? But then I want to switch the order of things, right? So first of all, to switch the order of the differentials, I get a minus. To switch the order of the multiplication of the coefficient functions, that's commutative. That's just multiplication of real valued functions. And then I undo the distributivity, and that gives me this wedge that. Of course, this is exactly beta, and that's exactly alpha, and there's a minus out front. So as you can see, alpha wedge beta is minus beta wedge alpha. So that's for one forms, all right? Now, so you might, I guess you could replace axiom 3 with this for an arbitrary one form. It's convenient for our discussions to go through this calculation. That's page 1. All right, so let me just write down, my intention here is to try to quickly go through the structure of differential forms in the wedge product in n dimensions over just Rn. And then we'll specialize to R3 where there's lots of special formulas that are really, really cool. Anyway, so 2. So a 0 form, let's just get some terminology down here. A 0 form is just a function. f, it goes from some subset perhaps of Rn to R. I mean, you could replace the domain with just Rn without much loss of generality here because of bump functions and junk. That's for another day. One forms, what do those look like? We just saw that. Alpha, so alpha 1 dx1 plus plus alpha n dxn, or I'm going to write it this way for now. Notice that the index is down. That's our convention. And then a 2 form, what's that look like? Well, they're basically like this, beta. So now we do a sum over I and j, and beta ij dxi wedge dxj. Now, in order to match up with what are called tensor coefficients, we put a half here. Now, the reason to put a half here, I can't really explain to you here, but if you take advanced calculus, you'll see why the half is there. That's a 2 form. All right. Now, this sum is over all values. That's not actually a basis expansion. In particular, if I write it like this, you have beta ij is equal to minus beta ji. That's a necessary thing for these coefficients here. So there's a linear dependence between, say, example 1, 2 and 2, 1. That's okay. We just have to keep that in mind if we work with this notation. The 3 form would be something like a sum over ijk, and then 1 over 3 factorial as it happens, gamma ijk, dxi, wedge dxj, wedge dxk, and then you see where this is going. A k form would be something like, gm, I need another letter, how about omega? Would be a sum, and here we need some kind of double index notation, so like I1 through ik, 1 over k factorial, omega I1, ik, and dx I1 wedge dx ik, that would be a k form, something of that form. Now, at times, it's nice to be able to write this in a more compact notation, so you could write something like this, I in the k indices over n dimensions. I mean, I don't know, let's put the n dependence right there, but if you did, there would be. And then you could write omega sub multi-index I dx multi-index I. And I wouldn't need the k factorial anymore because this is actually just the increasing indices of length k taken from n values. And so 1, 2, and 2, 1 aren't both in here. It's just got 1, 2, for example. So I don't need to divide by a factorial to fix it. This is the multi-index notation, sometimes useful. Okay, so these are what they look like. And again, if you take a p form and wedge it with a q form, right, you'll get a p plus q form. So here, let's look at that. Let's see here. So let's see here. So like alpha, wedge, beta. All right, and let's take. I'm gonna use the multi-index notation if you don't mind. So some, for example, I in, I'll do a p form. So alpha I dxi. Take that, wedge it with a q form. So beta j dxj. What happens? All right. What happens is you use distributivity. All right, and you get alpha I, beta j, dxi, wedge dxj. Well, how many differentials are there in here? This has p plus q differentials, right? So this is a so-called p plus q form. So, my goodness, so if you think about this, if I take one form, wedge it with one form, I get a 2 form. If I take a 1 form, wedge it with a 2 form, I get a 3 form. If I take a 2 form with a 3 form, wedge them, I get a 5 form. You see where this is going? Like, my goodness, it looks like we have infinitely many forms, right? Like, but there's a catch. In Rn, we can only have up to an n form non-trivially, because, why is that? Well, you know, if you look at, for example, dxi wedge dxi, you get minus dxi wedge dxi, right? So one of the fundamental lemmas is that the differential wedged with itself is 0. Or more generally, a one-form wedged with itself is 0. And that actually cuts down on what's possible, right? So if you think about that, then if you had dx1, wedge dx2, wedge dot 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 wedge dxn, that's kind of it. Like, I cannot wedge that with anything else. I've only got 1 through n to work with in our n, right? So this is an n form, and I can put a function out here, right? So this is an n form, and that's the largest degree form you can get non-trivially. This is the so-called top form. Okay, so for example, for R3, we'll have 0 forms functions, 1 forms, 2 forms, and 3 forms, and that's it. For R4, we'd have 0 through 4 forms, and so forth. Now, let me just get back to this purple calculation here. I want to see what happens for a P form and a Q form. How is the rule? We found alpha wedge beta was equal to minus beta wedge alpha for 1 forms. How does it work for P and Q forms, right? So if you look at this, I guess I can, let's see here, I can, what can I do? Well, if I want to switch the order of dxj and dxi, what do I get? Well, I'm going to argue that what I get, so if you think about that, I guess I should think about it on a separate page up here for a second. So dxi, wedge dxj, all right, so that would be something like dxi1 wedge da 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 wedge dxi, let's see, I was a P form IP, wedge dxj1 da da wedge dxjq, all right. And so what I want to think about is what kind of sign SIGN do I generate from moving the differentials like this one. I want to switch the order of this. I want to put dxi to the right of dxj. So I'm going to do that one, and let's see here how would I do that. I'm going to do it this one first. Move that over to here, okay? So if you look at that, I get minus 1 from this one, minus 1, minus 1, minus 1, minus 1. I get minus 1 q times, right? So I have dxi1 wedge dxi p minus 1, and then I've got my, I'm going to write it as dxj, because I'm tired of writing all those j's, wedge dxip, all right? And that generates minus 1, how many times? Well, q times. So minus 1 to the q, because it's minus 1 times minus 1 times minus 1 times minus 1 q times. Okay, great. Then, next step, I'm going to move this guy over to there, right? And that's going to give me dxi1, wedge da da da, wedge dxip minus 1, wedge dxj. Notice I just had to move this differential through dxj. That gives me another one of these factors, right? So now I get minus 1 to the q times minus 1 to the q, all right? And you keep doing this, all right? You just keep doing this. And as you can see, eventually you'll get dxj wedge dxi, right, after I move all the i's over there. And I'll have minus 1 to the q times minus 1 to the q, minus 1 to the q. How many times? Well, 1 for each differential in dxi. There are p of those. So there's p-fold factors here, right? P-fold product. Well, what is that? That's nothing more than minus 1, right, to the pq dxj wedge dxi. Now, so that identity is wonderful, and we can go back and use that here. So we get sum over I and IP, J and IQ, and I can switch the order of, well, I won't do it yet, fine. Fine, I will. Beta J, alpha I, that costs nothing because these are just functions for each multi-index I and J. And we got this snazzy -1 to the PQ factor, dxj, wedge dxi. All right, great. And then undo the wedge product, like undistribute in the same way that we distributed, and we get back to what? Well, everything's the same except we've got a -1 to the PQ factor, and it's beta wedge alpha. Aha! So there it is. There's the general commutation or anti-commutation rule for forms of so-called homogeneous degree. Homogeneous form is the ones we almost always consider. They're ones that every term in the differential form has the same number of differentials. Almost always this is what people are talking about when they're talking about differential forms, but in principle, of course, you can look at the totality of all forms over Rn, and that would give you the so-called exterior algebra. The exterior algebra would be formed from the direct sum of 0 forms, 1 forms, 2 forms, 3 forms, all the way on out to n forms. And in that context, the exterior algebra, the wedge product is actually an honest-to-goodness binary form in the sense that you take the wedge product of two forms and you get back another form. Of course, it's not a binary product on 1 forms because you take 2 1 forms and you don't get back a 1 form, you get a 2 form, right? So I guess the wedge product is a binary form on functions. The wedge product just reduces to multiplication of functions at the level of 0 forms, but that's kind of a special case. Anyway, so there's the general anti-commutation rule, ever so very important in everything we do. So one of the things it says is that if a form has even degree, it commutes with all other forms. Like 2 forms commute with 1 forms. 4 forms commute with 1, 2, 3 forms, and so forth. But if you have 2 forms of odd degree, generate a minus when you change their order. That's the wedge product. All right, so let's see here. What else can I say? Can I say anything else? I guess that was page 3 over here, our little lemma. Now, I'm going to put a note for myself later. C3, all right, there we go. All right. Now, so that's great, but why do we care about wedge products? Well, I would tell you that really what it is, I don't want to write this out right now, but here's another thing we can do with wedge products. Wedge products essentially encode the determinant, all right? So one way, for example, you could, let me see if I can zoom in a bit. Yeah, so the determinant, right, can be defined by the wedge product in the following sense. If I take this AE1 would be like column 1, column 2, column n. If I take the wedge product of the n columns of a matrix, then the coefficient of the top form with E1 through En, right, that coefficient is the determinant. You see this has the right properties to be the determinant. If I switch the order of the columns, I get a minus, you know. If any 2 columns, you can prove another thing. This would be a good exercise. You can prove if there's any linear dependence, and you have those, if you have those 3 axioms we started with, linearly dependent vectors must wedge to 0. So you could use the wedge product to study linear independence. That would actually be very interesting, because you could study, are 2 vectors linearly independent? Well, if their wedge product is 0, then game over, right? If 3 vectors are linearly independent, then the wedge product of them must be non-trivial. And so I can do that with any number of vectors in Rn, whereas, of course, the determinant is only a directly useful tool when I'm looking at a full dimensional set. In other words, like for 3 dimensions, I can test linear independence of 3 vectors with the determinant. Or in 2 dimensions, I can check linear independence of 2 vectors. And in n dimensions, n vectors, I need to calculate a determinant directly. But with wedge products, not so. I can kind of take half determinants in some sense. I mean, anyway, here's an example of the utility, though. So that's how you define the determinant implicitly. And then if you could prove the same lemma, there's a little lemma if you could prove it. If the identity also held for if you replace the standard basis with just a linearly independent set of vectors, right? If I could take E1, E2, En, and replace it with, say, V1 through Vn, if this identity was still true, homework exercise, then I can get the determinant of the product, its product of the determinants pretty quickly. So I apply this lemma with replacing E1 with BE1 and E2 with BE2 and so forth. Of course, if B is invertible, then the columns are linearly independent. So BE1, BE2, BEN would be linearly independent. And so there you go, I get determinant of A. But then I can look at this with the standard basis and apply the definition of determinant in this notation again. And then all of a sudden, bam, I've got the determinant of, with AB here, equal determinant of A times determinant of B. But this, by definition, in the current technology, is determinant of AB, and there you go. Product of the determinants is determinant of the products. Product of the determinants is, yeah. So if you remember how we did that in linear algebra, this is actually kind of cool because, you know, there's a stone cold calculation of it, and not too hard, really. Anyway, I shouldn't, well, maybe I should, but just wedge products are useful. Now, all right, so that's the other thing, of course, is it's just a more general algebraic construction you can look at. And so this brings us to the exterior derivative, all right? So how do you calculate the exterior derivative? Let me just show you an example, actually, kind of, let me show you a couple examples, then I'll give you a definition that was supposed to be in R. So for example, if I have a function, x squared plus yz, then I can calculate df is 2x dx plus z dy plus y dz. There you go. That's an exterior derivative. Of course, you're like, well, that's a total differential. Exactly. Example 1. Example 2, let's make it a little bit more exciting. Suppose you have a one form, alpha equals x squared dy plus y dz. So to calculate the exterior derivative here, d alpha, what you do is you take the exterior derivative of the coefficients and you wedge it with the forms, the differentials which are already there. Okay, but then of course that's 2x dx wedge dy plus dy wedge dz. There you go. That's the exterior derivative. Simple as that. Another example. Alright, so if I had, suppose I had gamma was, let's see here, x1 dx2 plus x2 dx3, fine, wedge dx7. There, that's weird enough. If I was to calculate the exterior derivative of that, I just have to say, oh, I may make this more exciting. Let's make this, here, let me make it more exciting. I'll make this the exponential. And I'll make this 2 to the x2 power. Fine, there. There we go. Now we're really got something. So, of course, the derivative of the exponential function is the exponential function. So I have e to the x1 dx1 wedge dx2 wedge dx7. That wrote along, right? So basically, my first step here really was to multiply it out. I'm thinking about doing that. E to the x1 dx2 wedge dx7 plus 2 to the x2 dx3 wedge dx7. So I just have to exterior differentiate the coefficient. So the derivative of 2 to the x2 power will be natural log of 2 to the x2 power dx2. Yes? Okay. I will do that. Okay. Okay. I'll get that. Okay, bye.
What is it? That?
Hannah, can you take the barbecue out of the fridge for me? Thank you. Out of the freezer. So there's a couple of examples of exterior derivatives. And so the general definition is not hard to state in our current notation. In the freezer. So for a K-form, gamma, it's just a bag. I1 through ik equals 1 to n, right? And you got your 1 over k factorial. Your coefficient functions, gamma I1, ik. Guys. Okay, guys. Please go back upstairs or something. Thanks for now. No, well, upstairs, yeah, sure, but... So here's a K-form. You cannot talk to me while I'm doing this, okay? So this is a K-form. The trouble of videotaping at home in the day. My goodness. I'm not sure this is sustainable. All right, so this is a K-form, right? And so d gamma is just some, over these indices. There's k summations there, right? And then you just do d gamma, right? Wedge dxi1, dxik. And now, of course, you can recognize there that this, of course, is a how many differentials are there here? Well, there's k plus 1, right? So this is a k plus 1 form. And if you go back to the examples we had on the previous page, you'll notice that, right, I had a 0 form, exterior derivative differentiate 1 form. I had a 1 form, exterior differentiated, I got a 2 form. I had a 2 form, right, exterior differentiate, I get a 3 form. And that's generally how it goes, all right? Now, a proof, something you can prove then is, well, what are the properties of the exterior derivative? So, first of all, of course, the exterior derivative of, say, alpha plus beta would be, it's still true, it's additive. If you have a constant, you can still pull out the constant, right? But here's the interesting one. If you have the wedge product of alpha and beta, where alpha and beta are homogeneous forms, all right? We're always thinking homogeneous. Then I have d alpha, parentheses, wedge beta, plus minus 1, and I'll use this notation, the degree of alpha, alpha wedge beta, d beta. So this is a graded product rule, right? And the grade is by the degree of the form. So here, so if alpha is p form, then I'm defining, right? I'm just defining this new notation. Alpha equals to p. Okay, that's all I mean by that. Nothing snazzy. Now the proof of 1 and 2, almost immediate from the definition and properties of the, you understand this d gamma here is exactly just the total differential, right? So like d gamma, let me use the multi-index for notation for a second here. D gamma I would just be the sum over j equals 1 to n, partial gamma I, partial xj, dxj, that's what that means, okay? So these two properties basically just follow from the ordinary algebra of the distributive property of wedge products and the corresponding properties for partial differentiation. The 3, though, the graded Leibniz, follows from a calculation very much like the one we already did to show that alpha wedge beta was equal to -1 to the pq beta wedge alpha. Of course, in our current notation, alpha wedge beta is equal to -1 to the degree of alpha, degree of beta, beta wedge alpha. That would be what that looks like in our current new notation, right? So the proof of 3 similar to that proof, and I'll let you work it out. Now, it's useful to just catalog a couple of special cases real quick for the exterior derivatives of 0 forms and 1 forms. So, so for 2, we already saw that, in fact. So for 0 forms, f and g, we have d of fg is, well, we could say gdf plus fdg. I usually like to leave the order the same, so I usually write this as df g plus fdg. That's my own personal preference. 1 forms, alpha beta, then we have d of alpha wedge beta is d alpha wedge beta minus alpha wedge d beta, because they're both 1 forms, and then you can think about how that would work for higher forms. So I'm not going to tell you everything there is to know, of course not, about exterior derivatives in Rn, but I will tell you one more general fact, and we'll talk about its implications a little bit before I specialize to R3. So an important thing to know is that d squared is equal to 0. This identity is so important. So the proof, did I ever zoom back out? Oh no, oh no, what have I done? Well, that was an unfortunate event. Sorry. Here's all those things I was just writing in the margins. Oh, I'm sorry. I'm very sorry about that. So, anyway, there's everything I wrote about properties and this. I probably was talking to myself, and sorry about that. Show must go on. Smaller children will soon be back home. All right, d squared equal to 0. So the proof of that, right? So you take d of d gamma, right? And so what that is that's d of, some, I'm going to use the multi-index notation. Let's say j, I'll say j1 and then I. And so that's like partial, and if you don't mind, I'm just going to skip the factorial. You could, whatever. I'm going to skip the factorial coefficient here and assume, this requires some interpretation, all right? So partial gamma I, partial xj1, and you got dxj1, wedge dxi. All right, great. But then you exterior differentiate again, right? And in the second, you get sum over, say, j1 and j2, appropriate multi-indices I, and then you get partial squared gamma I, partial x j2, partial x j1, dx j2, wedge dx j1, wedge dxi. All right? But the thing then is you're summing over all values of j1 and j2, all right? And so if j1 is equal to j2, it's 0 because dx_j1 wedge dx_j1 is 0. And then you have things with j1 less than j2, and you have things with j1 greater than j2. And there's the same number of them. And this coefficient is equal for like 1, 2 versus 2, 1. Or 3, 1 versus 1, 3. But these are minus. So if you think about that sum, this the fact that this is symmetric in J1 and J2, right? And the fact that this is anti-symmetric in the indices J1 and J2 forces that this altogether is 0, all right? And this is the famed d squared equal to 0 identity. There's been people who know more than I do who said that all of physics can be written in that equation. Well, whatever. There's a little bit more to it than that, but so a couple of simple examples. I'm going to use my notes here, if you don't mind. So one example, well, even if you mind, I'm still going to do it. Sorry. So one example here would be this one. So a force, right, is conservative if it could be written as the gradient of a potential function, right? Or we write minus gradient of phi in physics to get energy conservation. Now, in the language of differential forms, as I'll discuss more in the next part of this lecture, that really means that the one form corresponding to the force can be written as the minus the exterior derivative of the potential energy function, minus d phi. But if I have omega f is equal to minus d phi, that means that the exterior derivative of omega f is minus d squared phi, but that has to be 0. So then this gives me a simple criterion to use to test whether or not a given one form actually corresponds to a conservative force or not. So for example, for omega f equal to minus y dx plus x dy plus dz, I can take the exterior derivative, like so, and I get 2 dx wedge dy. That's not 0. Consequently, the force which corresponds to this form is not conservative. So that's a simple criteria. Another, I think, good example is given by Maxwell's equations. Maxwell's equations, of course, are the central thought of electromagnetism. They control how the electric and magnetic fields evolve one into the other through time. But it turns out that you can write electric and magnetic fields in terms of derivatives, spatial and temporal, of the so-called voltage function, which you're more familiar with from university physics, and also this vector potential. You can roll all of those things together into one potential one form in 4 dimensions in space-time. So that one form contains both the voltage function and the magnetic vector potential. And if you take the exterior derivative of this one form, you get dA. Well, dA would be a 2 form, right? This 2 form F contains in it actually the electric and magnetic fields, all right? So dA equals to F is actually a sneaky way of writing 2 Maxwell equations. As we'll see in advanced calculus, I show you that there. Anyway, the d squared equal to 0 identity here is interesting because it shows you that the choice of the one form potentials by far means not unique, right? This is known as gauge freedom. In particular, I could take any function of space-time lambda, and I can add d lambda to a, and say a prime is a new potential. So dA prime will be dA plus d squared lambda, but hey, d squared is 0, so d squared lambda is 0. And so we have dA prime is equal to dA, which means that a prime and a both generate the same F, and hence the same electric and magnetic fields. This gauge freedom actually turns out to be very interesting, and when you study it further, it allows us to view Yang-Mills theory in terms of the theory of connections on fiber bundles, principal fiber bundles. But anyway, that's a story for another day. My point to you is just that d squared equal to 0 is interesting. In fact, so. All right, in the next part, I will pick back up and talk about 3 dimensions exclusively. I hope this made some sense. If not, my apologies.